Our second speaker in this session is Divyan Agrawal from Tenstorrent Incorporated, where he's a senior director of RISCV cores. And he's going to speak about RISCV verification, the opportunities and the challenges. He's worked in core verification, emulation, silicon, DevOps effort at Tenstorrent. Worked across a number of ISAs, instruction set architectures, x86, ARM, PowerPC, and RISC-V for 20 years. So an impressive background. And on from scratch embedded design to the world's highest performance data center CPUs. Okay, thank you.
A lot. Thank you. So thanks for having me over. So let me talk through just the roadmap of what I want to address in this talk. Really split into two parts. Want to talk about CPU design verification. I've been in CPU combination of architectural modeling, design, DV, emulation for a little over 20 years. And the landscape changed quite a bit. For a while, CPUs were extremely interesting and hot in terms of field. Then there was a plateau. It was all about software, and now it seems like compute's growing again. And that's kind of generally the mission statement of our company, which is we are a next generation compute company. We look at CPUs and machine learning accelerators as sort of two facets of what is needed to speed up machine learning models and general purpose software. So I will talk through a little bit about just CPU design and DV philosophy and methodology that we use. Take a little bit of tangent, talk about RISC-V, and then try and connect both of them together into just a real world case study, something that we deal with day in, day out. Marketing slide, we are a machine learning company. High level roadmap, this is what we do. We've got 4 generations of products. The first one's out in the market, second one's getting released this year. And the next couple of generations we are working through right now. Really a combination of machine learning accelerators and general purpose compute. For the first couple of generations, we used off-the-shelf CPU cores. And then for our next generation, we're building a high performance RISC-V-based design from scratch. So just jumping ahead a little bit. So CPU design and verification. So our problem statement as a company was to go build a high performance out of order machine from scratch with a brand new effective ISA that a lot of folks in the team hadn't worked on before, which is really RISC-V, and then do it in a way where the design is parameterized. So from day one, our focus was what we have to deliver at the end is a design that can scale up across a wide variety of PPA targets. So performance targets, what power envelope it has to go into, and certainly how do we optimize area. And nothing comes for free. So if you have to focus on parameterization from day one, we made trade-offs and said, we're not going to try and optimize the heck out of every single interface that we have in the design. We need to make sure that our designs are flexible enough, even within the context of a CPU, that you can mix and match. That if you go change from a 2 wide to a 3 wide to an 8 wide machine, then you don't really have to make significant changes. And as DV engineers, I'm sure we can all appreciate that state space changes dramatically. If you go from a machine that's targeting microcontrollers all the way to that's targeting data centers, it's not the same space. It's also adds complexity, and it requires more resources. And that's one thing I think a number of speakers before me have talked about. You can't really scale up your engineering teams. You can't scale up your compute, your tool licenses, your emulation capacity at the same order. So how do we solve or look about this to solve this problem? Just a quick view of this is the out of order machine that we're currently working on. We've talked about this in various different forums. I actually want to skip through this and talk more about DV and design methodology. So when we look at a CPU, what we really see is different unique components. So for anybody who's familiar with the CPU pipeline, basic 5-stage pipeline, fetch, decode, execute, memory, and write back. Modern microprocessors have made that 30-stage pipelines, but the fundamental functionality is the same. That you get instructions, which can be compiled code from a high-level language, or can be assembly code. And you take that design, you fetch it, you decode and figure out what that operation is. This is where x86 differs from ARM or RISC-V, is you have complex instructions, and those complex instructions internally get converted into RISC-like operations. So ultimately, any modern microprocessor is executing really RISC-like operations. Then you go from there, you have your execution pipes. You can do your multiply, your add, your mag. Some designs have vectors, some designs have FFT, but ultimately it's all data manipulation, data math. And then eventually you go and say, I need operands, I need to go fetch it from memory. I can do it with whatever I have available, and then write the result back, then rinse and repeat. So for us, these are distinct pieces. They form a CPU, but we needed the ability to have these operate in a very independent fashion. So day one, I should say, day 21, whenever we got our act together, we decided to identify what our interfaces have to be. And the team that I work with, they've been doing high performance CPUs for 25 plus years. I work for a guy named Jim Keller. He's been doing CPUs for a while. And our mission statement as a CPU team at that point was trade off everything else except for interface clarity. And so we started with what are the absolute things that we need for clean interfaces. Because eventually this is a waterfall. It trickles down. It helps you for physical design. It helps you for certainly verification. It helps you for parameterization. It helps you for developing IPs. Helps you for software. I mean, and you trade off performance. So don't let anybody tell you that this all comes for free. So when you have to make decisions like this, the cost is taken at some point. But that was the cost we were willing to take. And we decided to have blocks implemented and partitioned in a way that they could be clean. And this is really our design flow. Is for us, each of these blocks are broken into different components. In some cases, we are actually able to pull out an RTL component and put in an architectural model or a performance model, and then operate in that fashion. So if I have to run a very complex workload, and I don't really care about how the branch predictor works in the design, I can pull in a performance model component and put it in there with the design, and that works. So I apologize for the font of this, but for those of you who've gone through any CPU or any ASIC design process, this is largely how it looks like. When you start off, you look at what market am I trying to target? What is my workload? So you go through a workload analysis process. Then based on that, you identify what is my PPA, what is my bonding box, what technology do I want to target, what kind of engineering resources do I need? Again, this is not just people, right? When we start planning or we start thinking about resources, we think about what storage do we need, whether our storage solution works with our design methodology. Do we have high IOPS, or are we more, I guess, we care more about tiered storage? So our design and DV teams actually sat down and did profiling of what we want to run. And we went through different storage solutions, whether we prefer NetApp versus Echelon, whether we want object storage versus tiered storage. This is very different. Typical engineering teams that's an IT problem for them. For us, it's not. For us, it's absolutely an engineering problem, because faster storage improves productivity. And if we want to do things with small teams, that is extremely, extremely important. We look at somebody talked about information infrastructure and methodology. So we look at what is the complexity of our environments, of our test benches, and how do we alleviate that complexity? What's the memory footprint for our test benches? So when we start doing that profiling, we have a goal. And in order to fit that goal, we have to see what machines do we use. Do we go with your standard cloud-based servers? Do we actually go and do profiling of what AMD or Intel machines do we need to use? So our engineering team, and again, this is, I can't say this enough, is engineering has to look at a broader problem solution. So we ended up looking at even what servers fit our need, and we did profiling. We took our, people are familiar with CI/CD. We look at our CI/CD runs or our smoke or curation, whatever we would call it, and say, this is my memory footprint. And so if I go and run this across 8 cores, 16 cores, 32 cores, what is my sweet spot, which gives the engineers the most amount of productivity? So we're trying to almost engineer this at a macro level rather than just worrying about a problem for what is our architectural spec and what is our test bench methodology. So once we go through that, that allows us to plan what kind of tools we need better, where do we optimize our problems. Then we go into the microarchitecture phase. We talk about design methodology. Number one goal is parameterization and interfaces, clean interfaces. So most of our RTL and DV and even PD methodology is kind of driven by that. So for instance, when we'll sit down with a physical design team and talk about what are the tile boundaries for implementation, they have a goal. They need to make sure a synthesis completes in 8 hours. Right? These are large designs. These are billion transistor designs. So if your synthesis has to complete in 8 to 12 hours, then how do you partition the design? Are your RTL and DV teams aligned on those boundaries? So this whole process, and it may seem like you're spending too much time early on thinking and talking about things which may not be as critical for a typical engineering team. Again, this is really more of a back-end problem, but the PD decisions impact RTL and DV and vice versa. So we go through that process, we go through microarchitecture, we really clean up our interfaces, then we go through the development process. You do RTL coding, you build architectural tools. If you're doing something from scratch, you're literally building your reference model with your performance model, with your RTL model. And there are a lot of trade-offs that you need to make because sometimes you need to take decisions without availability of evidence. I know we all like to be data-driven, especially as DV engineers. But sometimes that data is just not available. So you take some judgment calls, and then in a lot of cases, you go back and fix them. You go through your development process, and at that phase, at that phase, you actually start platform planning. What particular platform do we want this design to go into? And this is slightly different from workload analysis and the end customer. This is more about when we look at socket, when we look at package, when we look at what my reference platform has to be. Especially as a startup, we have to think through, unlike a large company, when our CPU or our machine learning accelerator is done, how does it fit in when it comes back from a silicon standpoint? How do we go bring it up? And so that work happens pretty much early in the phase. And then very standard RTL and DV flows. We go through coding, verification, and at some point, we start silicon planning. Eventually, silicon comes back, you go through post-silicon validation, you have customer samples. If there are issues, you go back respin. If everything looks great, you go and then eventually release a product. So this entire cycle is about 3 years. I've gone through multiple from scratch cores. It can be anywhere from 2 years to 5 years, depending on what kind of roadblocks you fit. But in our mindset, it's really overall process about 3 years. So the complexity here, by far the biggest one, is when you are at step 1 and you know this is going to be 3-year processes and there's going to be a lot of surprises. How do you work through this? And this brings us to just the verification complexity. So there are many views of how to do DV. One of them is give me an architectural spec. I'll read through it. I'll come up with a test plan. I will execute on that test plan. That would require me to build test benches, checkers, stimulus, coverage. And then once that's done, I'll find as many bugs as I can. Coverage will tell me I'm done. And then at that point, I say sign off. So that's one view of things. Our view of things is we started from the end. Is we need to get this out as a product for a chiplet. We need to get this out as potentially an IP. So what do we need to do that? Again, parameterization interfaces always at the back of our minds. But when you have to get this out as a product, start with an operating system. So literally the first thing that the design team focused on is how do we boot an OS, a real OS on our design. Not starting from writing a lot of bring up tests. Well, we did some initial enablement, but not focusing so much on bottoms up, but looking at the big picture. Because oftentimes when you're starting on a new architecture, you learn. and we wanted to give ourselves the time to learn, and we made mistakes and we went back and corrected a lot of them. I'm sure there's still some we have to correct, but you learn from that process. So we went through an OS, bring up cycle. We look at RISC-V is relatively new, certainly compared to the other, I don't even want to call them peers. People say RISC-V is everywhere. RISC-V wants to be everywhere. RISC-V is not everywhere right now. So we want to look at what is the application stack that we want to target. And we start with categorizing this application and say, what's the lowest level application beyond OS? And then we stage them out and take those applications and compile them into our environment. We want to make sure that we are ready to run them on the design when our design gets to that level. We start thinking about firmware. This could be power management. We are a compute company. We use machine learning models on our hardware side. We want to make sure that we have the capability to interface between CPUs and accelerators. Next step, we look at not test plans. We look at what do we need to do so that the first generation works. And so we start thinking about post-silicon. This is literally in this phase. When we talk about PPA planning and building blocks, we start talking about post-silicon then. I come from a world where there's so much effort put in the past on post-silicon debug and hooks that it sort of makes you even more paranoid about things. So we start with and think about how do we put in workarounds when the silicon comes back. We look at architectural workarounds, we look at microarchitectural workarounds. We actually start building components for post-silicon support early on. How do we measure performance? How do we measure power? A lot of this is in many places is an afterthought, but in those places, I'm hoping they have the latitude to deal with this later. We don't. So as a startup, we have to think about these things up front. And then we start talking about post-silicon. We work through it. We put together an actual silicon test plan initially. These are the components that we would need. And then we go backwards from that. Then we start thinking about design convergence. So for design convergence, actually, going back to product and IP, let me skip that. We'll come back to it. So design convergence requires bug hunting. Bug hunting requires diversity of stimulus. So it's great to have one stimulus generator. RISC-V has a lot of great open source resources, but are they enough for us to converge a high performance design? And so one of the initial investments we actually made is to start diversifying our stimulus avenues. We have multiple different stimulus generators that we invest on. Then you walk backwards from that is functional enablement. And this is where it becomes more of a collaborative discussion with the design teams. Okay, we are now bringing up the functionality. What RTL pieces will come in when? What DV test benches are going to come in when? And then walk backwards from that and say, now, what is your first step? How do we get through reset? How do we get through your first load? How do you get through working something end to end? How do you get your bypassing to work? And then obviously specification. So the point I'm trying to raise here is verification state space is not simply a function of an architectural spec and getting coverage sign off. It starts with a mindset, which is what product this is going into and what do I need to think about for that product to be successful. So this is lessons learned, and this comes from just not me. I've worked with a really talented team, just done this at Apple and AMD and Tesla and Amazon, and it's really what do we need to talk about. So DV workloads. We start thinking about, I mentioned what workloads do we need. If we are targeting an IP space, there are certain workloads that are important. If we target a server space, there are other workloads that are important. OS enablement. Linux is great. I strongly believe that Linux has a good parallel with RISC-V, and Linux proliferated being an open source ecosystem, and so would RISC-V. Parameterization. What do we need to do in terms of design and DV? So we start building our design in a way that the code is generated parameterized in a parameterized fashion. That's an interesting concept because now we have to talk more about that code generation. So in our design, we generate a lot of RTL, we generate a lot of DV code because we cannot afford to have parallel teams writing RTL for different IPs. It's essentially the same team that has to do it. We started talking about system level reference model. So we took an open source instruction set simulator, Whisper, and we've talked about this publicly in the past. And then we essentially started putting software models around it. QEMU was there. We worked a little bit with QEMU. Again, RISC-V is in a relatively early stage, so there's not a lot of performance optimization. And we wanted a little bit more control over how we want to speed up the reference models. So our overall strategy was to take our ISS, the instruction set simulator, and build a lot of software components around it. That allowed us completely orthogonal to the design to go and start running high-level workloads and start doing profiling. So again, goes back to connecting the product back into what we would need to implement in the design. So when you start running KVM on your instruction set simulator, that gives you a really good view of how KVM uses hypervisor extensions. What are the things that are critical for your design? Again, x86 and ARM world operate differently. So for example, on x86, for those of you who are from the CPU world, there are hardware A and D bits when you do page table accesses. There's a significant emphasis put on matching that functionality between design and DV. ARM is very software centric on hardware, the A and D bits. You keep that in your TLBs, but at the same time, you still kind of focus on the overall architectural correctness. For RISC-V, this was all a very new area. So we had to spend time looking at actual workload profiles to see where should we be investing our engineering effort. And again, when I see engineering, I talk in more general sense. Then we talked a little bit about debug visibility, spending a lot of time on it. Kind of mentioned most of these things early on, so I'm going to try and skip this before. So switching over to RISC-V. It's open. You don't have to pay anybody any money to use the architecture. ARM is not. x86 is certainly a very closed ecosystem, and I've worked on both of them. The one area RISC-V still has significant work remaining is really in terms of toolchain. And this is really where, if it has a Linux-like trajectory, it's going to do really well. From a DB standpoint, for those of you who worked on x86 or ARM, those ISAs have accumulated enormous amount of technical debt. You spent so much time in just supporting what was done 20 years ago that at this point, it reduces significant flexibility. If somebody's starting to write a from scratch test bench for an ARM or an x86 based design, you have to think about what decision was made for a transcendental operation 30 years ago. So RISC-V gives you that capability to start with a base ISA and wrap extensions around it. And this drives how you design, or this actually, funny enough, this also drives how you do physical design. Because you can start doing placeholders for some of these complex components up front and say, I will come back to floating point later. I know it's going to take more area, but I would treat this slightly differently. So overall, starting from a clean ISA like that really reduces the cost of your development. And then the impact of bad decisions made up front, because this is really, from scratch ISA. So let me see. This is really kind of the money slide, I'd say. Challenges that we currently have is RISC-V overall ecosystem. There's just general lack of silicon workloads. There are opportunities. There's a lot of work happening in open source, but I think there's the need to have a more coherent effort in converting some of the key workloads from x86 and ARM to RISC-V. I mean, when we go talk to customers, they'll really tell us we need a drop-in replacement. How do you get a drop-in replacement for something that's been around for 20, 30, 40 years? So that ecosystem around what is needed, for any of you looking to start a company, that's something. A lot of people right now are looking to go to RISC-V, but they are challenged because they don't know whether it's going to really be a drop-in replacement. If I'm doing a product, I don't want to have to deal with the risk that comes with a new ISA unless I'm provided a migration path. Stimulus generation, going back to, I guess, my DV roots a little bit, they just lack good stimulus. And there are a lot of startups in RISC-V domain, and a lot of those companies are trying to build something of their own. Large companies are trying to build something of their own. but the only way for RISC-V to get close to the other ISAs is to have more collaborative effort on building better stimulus. Deployment of software stack. In the x86 world, you go to a cloud vendor, they have a 10,000 core cluster, you can get quick turnaround feedback if you're certainly targeting a data center workload, not in RISC-V world. So there is lack of these things where you can go and try out your RISC-V stuff. And there's this work happening. Probably one of my biggest pet peeve here is there's a lack of a clean application programmer's guide. If somebody has to go and do RISC-V software development right now, there's just no clean way to do it. And anybody who's looked at the RVI spec, it's a big challenge. So anyway, I'd say this is the money slide. If anybody has any questions about how we are integrating RISC-V in the real world use case, I'm happy to talk about it afterwards.
Yeah. Okay, so there's a question over there. So
I'm sorry, go ahead.
Because you have so many, I mean, there are companies which are doing similar work. So what is the biggest challenge and how you feel that, Tenstorrent could be a differentiator?
So I guess there are like 3 or 4 different questions in there. So let me put a pin on the Tenstorrent as a differentiator because we're not purely RISC-V, we're a machine learning company.
Sure.
But just for RISC-V, I'd say the biggest challenge is lack of good, from a DV standpoint, lack of good stimulus. When your bugs start going down, a DV engineer actually starts worrying more because you expect the bugs to keep going down. So it's off the cuff, that's probably the biggest thing that keeps me up.
okay, thank you. We're going to have to finish there to get on the. Thank you.